Alrighty. Hello everyone and welcome to Computer Network Fundamentals, a short course presented by IT Masters on behalf of Charles Sturt University. My name is Guy Coward and I will be your MC tonight or today and for the duration of this course. Your mentor is Matt Constable, who you will hear from shortly. Before we begin, some housekeeping. All webinars for this course will be held at 8 o'clock Australian Eastern Standard Time, with recordings made for those of you who cannot attend on a given night. Despite this, if you can make it, we hope you'll attend the live webinars and contribute to a collaborative learning environment. On that collaborative learning environment, before we begin, a few words on Zoom's webinar functions. We encourage the asking of questions and the use of chat during the webinar, and there are two ways to do so that we use. We ask that you direct all course content related questions to the Q&A section, and there's an icon down the bottom of your Zoom window, and that you send all administration type questions to the support team in chat. So if the question is relevant to whatever Matt's talking about or what Matt has been talking about, we'll answer it in there. And if it's, as we can already see, questions in chat about when recordings are available, that's definitely something for chat. You can chat with panelists only, or that is to say Matt, Chantel and I, or to all of your fellow students as well, and you can make that choice by toggling through the drop-down box once you've opened the chat log. All panelists and attendees. There are usually some very experienced industry-based attendees who will be most helpful with any queries you have and quite often have great insights and can augment whatever Matt will be delivering on. We'll have Q&A sessions periodically throughout this webinar and all of the webinars, and I'll possibly interrupt if a question is particularly relevant. For those who've never taken part in a short course with us, IT Masters is a training organisation that exists as a partner to Charles Sturt University, who we work with to create and deliver a number of their master's courses. We also market those courses on their behalf, and these short courses are part of that really. We think and hope that the best way to market them is to give some of the content away for free. If we do a good enough job, then students will be encouraged to enrol in the full masters if it suits them. With that said, I really do hope that this course stands alone in its own right and is its own reward. We want you to learn some useful information in the next few weeks, have a bit of fun with Matt, Chantel and I, and hopefully make connections with your fellow students in the forums. Chantel is around tonight in an administrative and technical support role for IT Masters. She is also responsible for the learn.itmasters.edu.au website, which is where you'll find the other materials needed for this course, readings, discussion forums and quizzes. If you have any questions tonight or later on about the learn.itmasters course page, please feel free to contact us using the details on that page. And if you're struggling, at info@itmasters.edu.au. Next week, I'll talk a bit about CSU and hopefully give you an idea of what studying with them is all about. So if you have any questions about that, hold them and I'll hopefully answer those then. Anyway, here is Matt Constable, resident expert in all things networking and cybersecurity, Iron Man, senior lecturer and course developer, and just all around good guy. Looking forward to the next few weeks. Please welcome Matt Constable. And while he's introducing himself, I'll launch a poll as well.
Thank you, Guy. As ever, an awesome introduction, and thank you for your kind words. As I said, don't pump me up too much because it only leads to disappointment. Welcome, everybody. Excellent. Really pleased to see quite a few familiar names there in the chat box. Now, just be aware, I'll just let you know before I get started on everything networking, I'm not going to look at that chat box. So if you want to ask me any questions about the content as I go through things tonight, please use the Q&A function of Zoom rather than the chat, but feel free to talk amongst yourselves and obviously provide your input. As Guy alluded to earlier in that excellent introduction, there's going to be plenty of you out there. I can see the poll. There's quite a few of you that have had 5+ years experience in networking. So some of the topics that we're going to cover over the next 4 weeks might be well and truly familiar to you. For those that probably this course is probably aimed at those with 1 to 3 years of experience. We look at some things in a little bit of depth, but it's based around the CompTIA Network Plus certification, this particular course. So while we don't make any guarantees that you'll be able to take that certification exam at the end of these 4 weeks, you'll be certainly well on your way to preparing for the exam if you want to take that. And yes, we are still on the first slide. I'm just doing my preamble, but we're just about to go to the second slide. So let's get started. As you said,
Matt, just one sec. We'll go through the results of the poll because people
okay, go for it. Yep.
People in the recordings actually can't see them, so that's the one more.
You box cleverly.
Yep, one more reason to join us in the webinars. So the question was, how much networking experience do you have? Less than 1 year was 40% of respondents, and there was about 310 people responding. 1 to 2 years was 16%, 2 to 3 years, 11%, 3 to 5, 5%, and as Matt was saying, 5+ years, 26%. A lot of people I saw in the forums actually saying it's going to be really good to refresh my knowledge and sort of get a new insight. So that was really nice too. So I'll share those results on the screen now and then close that poll.
All right, so Rick's just put a point in. He said, my experience depends on what question you ask. My background is in telecommunications, i.e. radio. Yeah, absolutely, Rick, 100% correct. So even within, and it shows how broad the different areas are in the IT industry, that you can talk about a relatively specific area like networking and still have lots of different types of experiences within that field. So absolutely right. So hopefully though, whatever the case might be, whatever your level of experience is, hopefully over the next 4 weeks, you'll pick up some little tidbits or different ways to look at things, or even if you make contacts with other students and build some networks and share some knowledge around, then it's certainly going to be worth your while. Okay, so the short course, as Guy alluded to, part of Charles Sturt University, obviously based, this particular short course is based off the subject there, IT 526, an elective of our master's streams into networking fundamentals. And a lot of the topics that we talk about over the next 4 weeks are also part of that subject as well. So this is what we're going to look at this particular week, not necessarily all of this in this tutorial tonight. We will talk about a lot of these bits and pieces, but some of it will also be covered from the actual resources that are up on the online side as well. So you've got to take all the resources together in order to get the whole picture rather than just one or the other. So they complement each other beautifully. So there's a fair bit to cover, okay? Yes, it's an introduction, and that's a little bit about us and what we do and some tips for you in terms of your learning. And then we'll talk about the different networking concepts here. These little areas in red, basically, they're just points that I'll talk about more when the time comes with reference to labs and being able to give you some perhaps practical exercises which to build some skills in those areas if you haven't already got them. So that's me. I'll let you read that at your leisure. Basically, I've been around for quite a while now in the IT industry, worked in lots of different fields in terms of technical fields, but also on both sides of the customer, integrator fence, government, all sorts of different things. So wealth of knowledge. So people tell me, but obviously I don't have all the answers and I don't profess to. So you guys out there obviously represent a wealth of knowledge as well. And it's really important, really important in these short courses that you interact as much as you can with each other through those discussion forums. You will find that you'll learn as much off each other as you will off these tutorials and the resources we provide. And to be able to build those networks and strengthen those learning opportunities is something that you certainly don't undervalue. Webinars, obviously if you're here you'll know we run Tuesday evenings at 8 p.m. Australian Eastern Standard Time, and available access to those recordings. So we record, and those recordings will be available to you within 24 hours. Easiest way to contact me is probably via the course forums, okay? And it's a preferable way because that way if you've got any questions about the content that I talk about or any points that I make, then if you put some questions up on those forums, everyone can share in that discussion rather than just contacting me one-on-one. So preferable to do that, particularly with these short courses. In terms of your learning resources, there's going to be various learning resources popping up from time to time on the short course system as we head through the weeks. The first week, all the content for this week is already up, and you should be able to access that. Remembering that there's a quiz each week which has 5 multiple choice questions on it. And you can, I believe, if my memory serves me correctly, you can go through that as many times as you like to get practice. There'll also be some lab tasks. So some practical labs using the Cisco packet tracer application. So that will be made available, a version of that will be made available to you to download, as well as the labs. And then there's a range of individual and forum activities to help you learn. So some questions you need to ponder, and I'd encourage you to post answers to those questions to the forums, and then go and answer someone else's, and you know, generate some discussion. The more you engage, the more you will get out of these 4 weeks. So just some study tips that I think I always like to mention at any time that I do a short course, or even in the subjects that we teach through IT Masters. They're really, really good tips to help you better with your learning, okay? So I'll let you read through them basically in your own time, but they're all pretty self-explanatory, except maybe the second last one, the one of being beware of familiarity. Just be wary that just because you are familiar with a particular topic, or you may have seen it before, doesn't really mean necessarily that you understand it in depth. So in terms of, you know, if you're doing university subjects or you're doing certification exams, that can sometimes trip people up because they think might hear a term, say EIGRP, and they say, yeah, I'm familiar with that. And then when it gets to the nitty gritty of it in an assessment piece, or, you know, in an interview, in a job interview, for example, when you're asked in-depth questions, you may find that you fall a bit short because you're familiar with it, but don't really understand how it works. So measure yourself always on that level. Think about, am I familiar with something, or do I really know it? It's a really cool way and a really good way to determine your level of understanding, and then understanding how far you need to go with your own study. Okay, so let's get to the content. We've got quite a lot of slides to get through, and I will apologise in advance, and I apologise to Guy and Chantel, because they'll know that this is coming, but I'll apologise anyway. I am a little bit notorious for going over a little bit in time in these short courses. I will try to keep to the hour-ish as best I can, but I'll apologise to everyone in advance.
I can tell everyone right now it will not be an hour, and I think that the charitable interpretation is generous with time.
Thank you, Guy. Thank you. I like the way you put that. Oh, so let's get on with these lots of slides. So networking concepts, they're the topics. Let's have a look at them. So networks, how are they used in the modern world? So typically they provide network services of some description. So in other words, it's a resource, a network resource makes available to its users. So it's something that a network delivers to the users, which can include applications and any data associated or provided through those particular applications. If we break the applications down into 3 basic types. Now, remembering sometimes your experiences may differ from what we talk about on the slides. These slides are based off the Network Plus course. So we're sort of keeping to the content in there, but it's not exhaustive. But if we break it down into 3 basic types of applications, we have our client server applications. So we have a client, normally a desktop or a bring your own device, or a laptop or some other connection point that connects into a server environment or a cloud environment, as we'll look at later on. And those services are delivered over that link somehow. Now, obviously at that level, we're not talking about the actual network architecture side of it. We're talking about the applications that run over it. File and print services, obviously really, really common, and the multitude of communication services that exist in our contemporary world. And we have a look at those more as we progress through the slides. So client server applications, client computer requests data for a service from a second computer, normally called a server, but it could be a cloud environment or a whole group of servers. And then that information is passed back to that requesting client. So pretty straightforward. Okay, so generally a one-to-many type relationship in terms of the actual communication path between the two endpoints. And there's some examples of some popular client server type applications, but there are many, many, many more that I'm sure you would be aware of. So any sort of web services, email is obviously really commonly used ones, file transfer protocol, so FTP, telnet services, maybe not, depends on the context whether you're going to use telnet or not, but it's an example of a client server application. It's mainly one of those things that we use to access remote hosts for management type purposes, and in a lot of areas now, because telnet is not an encrypted service, we use SSH, but similar sorts of things. Remote desktop and obviously remote applications are other client server applications that are floating around. And this is just an example, a quick image to put that in a pictorial format. So we've got a user on the left here. Let's turn my laser pointer on while I remember. So we have our user over here who has a web browser request to that particular URL. He traverses the internet, hits the web server, and the web server then sends that requested page back to that user. So a fairly basic form of communication. Here's another example. So someone sending an email. So we have our sender on the left here. He sends it. Now don't worry too much about the acronyms here if you're not already aware of what they are. Basically, they are protocols that are involved in the communications channel in email. If you don't know what they are, we'll talk about them a little bit more in depth as we progress along tonight. Suffice to say, we have a sender sends an email to a sender's email server. That server then will pass it on to the receiver's mail server, who will then pass it on to the receiver. Now that's really, really simplified. It can get much more complex than that depending on how many email servers you have in between the sender and receiver. But that in a simplified nutshell is what email looks like. And so again, an example of a client server application. In terms of file and print, file services is basically just the ability of a server to share data files and disk storage space or some type of storage space. So somewhere that you can save your work files and somewhere that you can retrieve them from in its simplest form. So the servers that do that are called file servers, classified as file servers. And print servers can be an adjunct to a file server, although it can be a separate server completely. And they simply have the ability to share the printing resources of an enterprise across a network. Okay, so you might set up all your printers or your Windows printers, for example, on a particular server, and then they're shared out from that one central location, rather than have to go and point all your desktops at individual printers all around the place. We just point them to the server and everyone's nice and happy. And basically the advantage of that, using that particular printing environment, is that you have that less time spent on maintenance and management of your printing system. Communication services, okay, convergence. Ooh, there's that buzzword from a few years ago, and it's still buzzing around. And basically all convergence, if you've heard that term before, all it basically means is using a single data communications platform or network to deliver different types of communication services. So it could be voice, as it says down here. It could be conversational voice, so voice over IP that you use with your normal IP phones, streaming live audio and video, or streaming stored audio and video. So basically it boils down to data, so normal everyday file server, SMTP, mail, I won't get into that much depth yet, mail, web traffic, those sorts of things. And then you've got your voice and video that fits on top of that. Now that can be real time or it can be recorded and then played out afterwards. Another one that you've probably heard a lot of over the last few years is unified communication. And all that basically means is that it's reference to a centralized management platform of multiple network-based communication systems. That's all it really means. So for example, if we look at the classic example of, say, Cisco's call manager platform, so they have their call manager platform, which is for IP voice. You might have some file servers mounted in there, and you've also got their voicemail system which integrates with email. So you say if you've got an Exchange email server, you've got the Unity voicemail system which will integrate in with that. So that whole shebang all put together is basically centrally managed as part of a unified communication system. And that's all it really refers to. It's just a management platform for multiple network-based communications. So they sound a bit buzzwordy and a little bit interesting, but it's pretty simple when you look at it. The important thing to remember about voice and video is that the transmissions are really, really sensitive to delay. It's not good if you have delays in your traffic or breaks in your traffic. So you're losing part of your traffic as it's transitioning across the network, or there are parts in the network which are slowing it down and so it gets there late. Okay, that will really play havoc with voice and video. More so with video than it does with voice, because as humans we have this interesting capacity to be able to listen to broken sound and somehow, or garbled sound, and somehow make sense of it. So long as it's not garbled hugely, if there's a little bit of latency or a few drop packets here and there, our own auditory systems can handle that. Video is a different thing altogether. If you start losing blocks of video as it's coming through, it gets really pixelated and really ugly very, very quick. So we need to be understanding that voice and video are very sensitive to delay, and they are considerably less tolerant to issues with your network architecture. So in order to help get over those couple of boundaries or problems, we use a thing called quality of service. So quality of service is basically a set of parameters, set of protocols, a set of systems that allow us to, as network engineers, if we're network engineers, to stream our video and voice with a higher priority than other traffic. So in other words, it gets better service on the network. It gets through first, gets through faster. And so we lessen the delay and lessen the likelihood of loss. That's not to say that we won't get loss, we won't get delay, because again, it's going to center around how fast your network is, how much bandwidth you're willing to pay for, because let's face it, it costs, and how you've engineered your network. So there's many, many, many things to consider, but in a nutshell, QoS is one of the tools that we can use to help get over these couple of problems. Bandwidth as a term is something that we would have heard before, and it's basically the amount of traffic or the data transmission activity on a network. That's the way we're going to talk about it. So if we talk about something 10 meg in bandwidth, it uses, at any one time you can use a maximum of 10 meg of bandwidth. Again, we'll look at these. These will start to make more sense. For those of you that are not quite up with what bandwidth is and how it works, it'll start to make sense as we get into some examples and we talk more about the technology as we go along. So in terms of controlling network access, there's a number of terms here that are useful to understand. So a topology is basically the plan or how parts of a whole network fit together. The term physical topology then applies to the hardware that puts a network together, okay, that facilitates a network that's put together in order to provide that network topology. A description of how computers and any other device, whether it's printers or multifunction device or routers or firewalls or whatever else, cables fit together to form the physical network. The logical topology is slightly different to that, and that really is more related to the underlying software and how access to the network is controlled. And we look at that in a little bit of detail as we go through in the next few slides. So in a nutshell, it's how users and programs initially gain access to that network, okay, which may be slightly different from some of the other definitions you've heard for logical topology, okay. But hang with me, it'll start to make more sense as we go along. Network operating system basically controls access to the entire network. So what we're really talking about there is a network operating system, say like a Novell NetWare, for those of you that are old enough to know what that is, or Windows or some sort of Linux system that provides that access to the clients or the end users. Okay, so that's a network operating system we're talking about in reference to servers, okay? There are other forms of network operating systems as well. So those that run on routers and switches and firewalls and load balancers and proxy servers, okay? And they're all categorized as network operating systems, but they all provide slightly different features and slightly different things, okay? Just to make it confusing for us. In terms of the types of networks that we can put together, so we've spoken about client server, we can also have a peer-to-peer model, which is very simplified and typically only used for small organizations. Okay, so peer-to-peer is basically where we have the operating system of each computer is responsible for accessing, controlling, oh, that's a spinnerism for you, controlling access to its own resources. That is, there is no centralized control. So we don't have a single server which has all the accounts and all the access rights set up on it, all the security set up on it. It's the responsibility of each computer within that peer-to-peer network to look after itself. In this case, the computers are just called nodes or hosts, and they just simply form a logical group of computers and a logical group of users. And they share resources between each other and may prevent access to certain resources as well. So not really that different from a security perspective to a client server model. There's still the concept of sharing and not sharing, but just done in a distributed fashion rather than a centralized position. And in this case, each computer has a Windows, if we're talking about a Windows network, or a Linux or whatever operating system you're using. Each computer will have a local account associated with that computer that is used to access the peer-to-peer network. Whereas in client-server relationship, generally all the accounts are kept on a centralized security server, whether it's using Active Directory or eDirectory or whatever, some sort of LDAP directory, and then users will log into those accounts using a local computer, but they don't necessarily have an account on that local computer. So that's an example of a peer-to-peer network, and you see they're just a bucket load of different operating. So we've got Windows 8, Vista, 7, Ubuntu desktop, and a Mac OS, and they're just all sharing resources together. I think what you can see from this clearly is that there's lots of links. It's basically a full mesh network, which makes things a little bit more difficult to manage and to look after. So there's no centralized point through which you can easily manage things. It's just higgledy-piggledy. So the disadvantage of that, of course, is it doesn't particularly scale well. But before I get into what the advantages are, we'll just skip to the next slide because I'm pretty sure that's where the advantages and disadvantages are. Aha, I boxed cleverly. So advantages of a peer-to-peer model are that it's really simple to configure because you simply just plug things into a switch or some other connection device, or if you're using wireless, you can talk to it, or you could potentially use infrared. I have used that before in the old days. If you want to go really old school. And it's really simple to set up, and it's not very expensive compared to other types of networks. You don't have to necessarily worry about structured cabling. You can just run patch cables across your desk if you want to do that. And it can be really cheap and easy to implement. However, the biggest disadvantages are it's not scalable. So if you've got more than really a handful of devices, it's probably going to get pretty messy pretty quickly. It's not necessarily secure, because we have no centralized security model. So you may have some visitor that might come in and jump on your wireless network or jump onto your physical cable and somehow be able to easily gain access to the resources that you've got shared out. Whereas in a centralized client server model, that's less likely to happen, not to say it's impossible, but less likely to happen. And certainly not practical for large installations. So if we're talking about enterprise networks, peer-to-peer model is really not going to work. By comparison, client server, as I said, we have resources managed by a network operating system by some centralized directory database. So it could be Windows, Active Directory, for example, in which case you'd have a Windows domain, which is just a logical group of computers that a single Windows server provides control over. Active Directory is typically, well, it is in a Windows environment, it's a centralized directory database that contains all of the user account information and computer account information and security that branches across all of the resources that are shared out. The other thing it provides is a global account. So that is, you can use it once you're assigned an account in a client-server network model, you can use it anywhere across that client-server network. So you can be at any site, whether it be in the same country, the same state, town, could be over the other side of the world, doesn't matter. You can use that same account wherever you go. So that's right. User can sign on the network from any computer on the network and gain access to anything that they have the security clearance to actually access. In this case, clients don't share resources directly with each other. Everything is short, although you can technically, but in most client-server network models, the best practice is to provide access to all resources through that centralized access repository. So whether that's a single server or a cloud environment or a big cluster of servers, everything is stored and shared and offered. All the services are offered back through that same system. And there's an example of it there. So in this case, you can see it's a lot cleaner, isn't it? So yes, we've still got different operating systems. In this case, some Windows boxes and a Mac OS. We have our domain database here, which has got all our user and computer accounts on it. And we have a Windows server. In this case, yes, it's a simple client server architecture, but it's a client-server architecture nonetheless. You can see here we've basically got 1, 2, 3, 4, 5 connections back to the server. Now, obviously, that's not drawn exactly how it would connect physically, but that gives you an idea that it's certainly a lot simpler and a lot cleaner, a lot tidier and easier to manage than the peer-to-peer model we spoke about just earlier. So in this example, the network operating system, NOS, is responsible for these following tasks. So it manages the client data and resources. Okay, it ensures that only authorized users are allowed to access that shared data and resources. It will control the user file access. So in other words, not only direct access to read it, but also write, delete, change type access restrictions. Restrict user network access, so similar. Dictates computer communication rules. So again, it's managing that information and communication flows, not just between computers and the server, but the user and servers and user and computers and user resources. So all the resources and services that it manages are all managed using the same security database. Easy to manage, easy to deploy. So server examples could be anything in the Windows family, all the way from I've still seen some Windows 2003 servers floating around. There's probably some NT still out there somewhere, all the way through up to the current iteration. Ubuntu servers or any Linux variant or Linux variants, if you want to say that. Red Hat Linux, another example. So there's plenty of, and one that's not there is Novell's eDirectory, Novell's NetWare using eDirectory, which is, I still believe, there's not a lot of it around now, not as much as there used to be when I first started, but certainly bits and pieces of it around still today. So there's a number of different client operating systems. Clearly Windows seems to be the most dominant now. So servers, in terms of what we need to provide in terms of resources, servers that have network operating systems installed generally require more memory, more processing power, so bigger CPUs, and larger storage capacity in terms of disk or network array storage than typical PCs. And generally they're equipped with some specialized variants of hardware just to provide network management functions and faster processing and delivery of information to requesting clients. If we compare the advantage of client-server to peer-to-peer networks, we've got user credentialing is assigned from a single place. So it's all managed. User security is basically contained in one place, easy to manage, easy to see. We can have multiple shared resources, again, accessed via centralized control methodologies. Central problem monitoring, diagnostic, correction capabilities. So you can see those first 3 points are all about it's being centralized, it's easy. It's in the one spot, it's easy to manage, easy to look after. And lastly, it's simply more scalable. Okay, so you can add more users to it. You can provide more services to your users than you can with a peer-to-peer network. So if we look at that there, again, that's similar to the previous diagram we looked at, but this one is showing more the physical connection where we have a network switch in the middle. Looks like potentially an old 3-com switch by the look of that, by the shape of it. That's showing my age now, isn't it? And my geekiness. We have a Ubuntu desktop, some Windows boxes, a Mac OS there, a printer, all hanging off the one switch, and away they go, they talk to each other. Interesting, there is one thing, oh, no, I won't say that. I'll leave that for the next point. So LANs and their hardware. So in this case, if we just scroll back to this slide for a second, this switch here represents the LAN or local area network. Okay, so up until now, we've talked about the server models and the software models. So client server and peer-to-peer are the two models that we looked at. Now we're going to branch off and have a look at that, the next layer down. So that network hardware, the network architecture. In this particular diagram here, we've only got the single switch. So it's a pretty simple network. So LANs or local area networks are a network or a communications architecture that's usually contained within a very small space. So such as a single office or a building. A device such as a switch, which is the device that we just looked at, provides access to network resources to clients and to and from servers using one of its ports, so multiple ports. So switches typically, most of them start, even if you get a really small switch, they start at around about 6 to 12 ports. But enterprise level switches will start minimum sort of 24, 48 ports now. And each one of those ports provides a link that can be used for communication of data. We'll also talk about some of the topologies. So a star topology is just a way in which a network can be physically built. Okay, and it looks like a star. So if we look at this one here, this network picture here, this sort of looks a little bit like a star. If you think of the switch as being at the center of the network, we've got all these little cables out to the side. If we join all those points up, you can sort of see it looks a little bit like a star. So they call it a star. It has a centralized point, and the light, if you like, or the cables radiate out from that center point. So it's analogous to a star. I don't know who came out with that, but it wasn't a bad analogy. And then we have this concept of a network interface card or a NIC. So please don't write NIC card or say NIC card, because that's saying network interface card, and that really, it gets on my goat. If I had a goat, it would get on it. So network interface card or just NIC, that's a cool networking way to say it, not NIC card, okay? A bit like ATM machine, but sorry, I digress. So simply a NIC is a network port used to attach a specific device to a network port on a switch or some other central connection device. So a LAN, a local area network, can have and generally does have several switches connected together. Great. The more switches they have, the more ports we have, the more people can join in the fun, and the more people can access our information, subject to security restrictions, of course. There's a section of the network or the LAN which is called a backbone, and that's basically, and we'll have a look at that in the next slide. So I'll just quickly explain it and we'll whip on to the next slide and it'll make a little bit more sense. So the backbone is really just a central conduit that connects all of the segments or pieces of the network together. And generally that backbone will be a high capacity, high speed area. Okay, so it may have bigger switches, more powerful switches, and faster structured cabling systems inside that backbone to make it faster, because all traffic is going to transit across that backbone. Another example of a topology is a bus topology, which I think is on the next slide. So where basically we connect multiple switches together just to form a daisy chain. Okay, it's like a daisy chain. Okay, it's called a bus topology. Each switch is connected to computers via a star topology, making it a star bus topology, just to make it more confusing. So we'll see how that works on the next. In fact, you know what? I think I might just go to the next page because it's probably easy to look at. So there it is in pictorial form, better than words any day of the week. So we have 3 switches joined together. Okay, this is the bus configuration. Okay, that's a bus topology because it's just a straight line. It's a linear topology. But if we look at how the computers connect into these switches, that's then a star topology. So each switch is a star topology, but the interconnection links form a bus topology, and so it becomes a star bus topology or a hybrid topology, just to be even more confusing. Cool. Next bit of really clever device and that we need to talk about is a router. So the routers are a really clever device that basically build the roadmaps for our network traffic to travel across. Routers manage traffic or the passing of traffic between 2 or more networks, and they help you to find the best path. So you can think of them almost like a network GPS. They can and are often used in small home networks to connect you to the internet. So your DSL router, you would have heard the DSL router or Wi-Fi router terminology. That's what it does. Routers simply connect networks together. Now, obviously in the home or in a really small office, okay, that can be pretty simple. So it's just a single router which connects 2 single networks together. But in big environments, you can literally have hundreds or potentially thousands of networks connected through routers. So they can handle a lot of different traffic. As it says, industrial grade routers can have several network ports, and those ports can be physical or they can be logical. Okay, so you don't necessarily have to have physical ports on a router. They can be logical ports in memory. Let's face it, everything's virtualized nowadays, isn't it? So that's no difference. The difference between a router and a switch is that a router acts as that conduit between different networks. So different, if you want to say that's analogous to different IP address ranges, different physical networks. There's also the concept of VLANs, which will come up in the next couple of weeks as well, which will help to build those connections for you. And that's basically what a router looks like there. So we've got this big chassis, that's an awfully big chassis-based router for a very small network, but be that as it may, we've got the router in the center here, connecting off to 3 switches, and then the network stations attached to those switches. So in this case, we've got 3 separate networks that are connected via that router, or 3 separate LANs which are connected via that router. We then have the concept of metro area networks and wide area networks, okay? And really the distinguishing feature between all these different types of networks, so LANs, MANs, WANs, or a thing called a CAN, a campus area network, is really just the geographical spread, so how far they go. So a logical area network usually contained within a single site or building. Metropolitan area network is just a group of connected LANs within a slightly larger geographical area, so it might be within a town or a city or a central business district. It could actually be within just one single physical site, but that site is really large, so think of a university network. So in that case, it's generally called a campus area network rather than a metropolitan area network, because it's still contained within the one site. It's just a very big site. You've got these individual LANs that are connected in each building, and then they connect via backbone fibers to create that, or backbone cables, I shouldn't say fibers specifically, that will then form that campus area network. A wide area network then takes it one step further. So that's just a group of LANs or local area networks that are spread over a really wide geographical area. So that is generally in between, so intercity, interstate, intercountry, or intercontinental. Okay, so we're talking about really long distances that then use subterranean or microwave or some other methodology to connect across vast distances. And again, I think we might talk about that later on tonight, actually. So MANs and WANs often use different transmission methods and media when compared to LANs. Okay, they're generally much lower speed in order of magnitude of 100, sometimes more depending on what you're going to pay for, and generally you will outsource those. So MANs and WANs are generally something that you outsource to a provider company rather than building it yourself within your own enterprise or own company. We then have a personal area network, which is just tiny. So you're talking about things like Bluetooth and infrared and those sort of really short distance communication protocols, okay? Not very far at all. So less useful in a enterprise architecture sense. So that's an example of a WAN. So we've got a couple of routers. We've got one in San Francisco and one in Philly. We've got a link between them. What that is, we don't care at this juncture. So obviously between San Fran and Philly is a fair distance. So that's a wide area network. But on each side of that wide area network, we have a couple of LANs that are connected. In this case, we've got a single LAN, LAN A, but it's in a bus topology or a star bus topology. Remember, we've got our stars to the switch and then our bus topology between the switches. And then on this side off the Philly router, we've got the same over here. So we've got two LANs connected via a long distance haul link. So that then becomes, collectively, that's then called a WAN. And that terminology of WAN does include the LANs as well. So even though this link between the two routers is classified as a WAN link, in general, if you said WAN, you'd be talking about the whole structure there. Okay, now to the really interesting part. Okay, I know you've been waiting for this, and here it is. This is like a sledgehammer to the skull. So we have a 7-layer OSI model. Okay, now the OSI model is one of the most undervalued piece of theory that you'd ever come across. It also can be mind-numbingly boring, so I'll try to get through it as best I can and make sure you stay awake. OSI stands for Open Systems Interconnection. It's a reference model, okay, and I'll explain what that sort of really means in a minute. It has 7 layers to it, and it was basically developed in order to provide a reference schema for the building of communications protocols and for network communications. Okay, so it's basically a reference model. It's a blueprint for how you put networks together or network communications together. It was developed by the ISO, so the International Standards Organization. I think it's or the French equivalent thereof, although I can't say the French, so please don't ask me to. In the 1980s, so it's quite old. The layers are numbered in order, starting with layer 1 right down the bottom, and that's called a physical layer. So if we look at just the names, from 1 to 8, they're called physical, data link, network, transport, session, presentation, and application. And if you haven't heard of the OSI model or you're not familiar with it, as a networker, it is one of the absolute must-be's to have in your skills armory. Okay, you must understand the 7-layer OSI. Don't have to understand all the intricacies of the actual standard as it's written, but it's really useful to understand what happens at each of the layers so that you can better design networks, troubleshoot networks, and support networks. In particular, as network people, we look at mainly the first 4, so physical, data link, network, and transport. As security guys, we go a little higher, but network guys can keep to those bottom 4. And as I always say, you know, and it isn't I say it, but it's not my saying. If you don't know, if you don't know that much about 4 layers, and it doesn't matter if you've got 7 or 15 or 20 or 30, we really need to understand those 4 layers. So that's diagrammatically what it looks like. And yeah, I guess it can be, you could think that's a little bit confusing if you've never seen it before, and in fact, indeed, it probably is. The main things that we want to point out here, and if I turn my highlighter on again, are, as networkers, as I said, we really only want to know about these, you know, sort of brownie colored layers here. So physical, data link, network layer, and transport. What happens above that is certainly important in the overall scheme of communication, but we're not going to worry about it too much as networkers. Okay, that's for other people to really work with, but we do need to have an understanding of how it works. You can see down the right-hand column, these are nice little tie together. So we can see that physical and data link layer really exist at hardware layer. They're a hardware abstraction. So hardware and hardware protocols such as Ethernet and Wi-Fi standards, if we talk about it from a network perspective. And the network interface card there, that, you know, that's where layer 1 and layer 2, that's their meat and drink at that hardware layer. Then layer 3 and 4, they start to delve into the operating system. So layer 3 and 4, we're talking about protocols like IP. So TCP, so IP, so our IP addresses, all our IP addressing and our routing is done at that layer. Okay. Also protocols like ICMP, which is basically our pings, and ARP, Address Resolution Protocol. Now, if you don't know what that is, ARP is sort of like, it's that lower level DNS. Okay, so DNS allows us to translate between IP addresses and friendly usernames or friendly web names. ARP is a translation between IP addresses and hardware addresses. Okay, so it goes the other way. And we'll look at that in more detail as we go along, but not just at the moment. Then layer 4 is where TCP and UDP live. So the TCP part of TCP/IP. UDP is a sister protocol to TCP. There's some slight differences between the way the two transmit, but we'll delve into that more when the time comes as we get along a bit. For the moment, we just need to understand that we really need, there's 7 layers in the OSI model, and the bottom 4 are the main ones we need to know about. So that said, the application is the top layer. Now, someone earlier on in the chat alluded to layer 8. So layer 8 is the facetious layer, if you like, which exists above layer 7, and that's generally that interaction between the application layer and the user. So layer 8 is typically the user. And as we know as support people, that layer 8 level is where most of the problems actually occur more often than not. He says with tongue in firmly in cheek. So application layer. I'll just quickly get through these first few, and then we'll spend a little bit of time on the bottom 4. So application layer really just describes the interface between two applications on separate computers. Okay, the application layer protocols are used by programs, so things like your web browsers and your FTP clients and your email clients. They generally fall into 2 categories. So they either provide services to a user, such as a browser, a web server, or they're utility programs that provide some service to a system, such as simple network management protocol. So it's a management protocol that monitors and gathers information about network traffic relative to that particular host. Okay, so they either provide services to a user or services to an underlying system. The payload at the application layer is data that is passed between the applications or user programs and the underlying operating system. So it's high level stuff. It's come straight from the applications. The presentation layer really is one of those layers that you don't tend to have a lot of need to talk about or discuss in any sort of troubleshooting, but it's basically responsible for reformatting, some compression and or a little bit of encryption in a way that the receiving application can read. So for example, an email message can be encrypted at the presentation layer by either the email client or some plugin on that email client or the underlying operating system. Okay, it's not generally one that we deal too much with in any sort of form other than maybe at an application development area. The session layer describes how data between applications is synchronized or recovered if messages fail for some reason. Application presentation and session layers are intertwined and are often difficult to distinguish between them. So what that's basically saying is the services and processes that those 3 layers provide are very closely related. And so it can be very difficult from a troubleshooting perspective to determine what's happening where. And that's one of the reasons why often we don't worry about dealing with these upper layers. In most cases, in a vast majority of cases, the issues that we will deal with day to day will occur in the bottom 4 layers. Anything above that is going to be definitely more complex and difficult to troubleshoot. At this layer, most tasks are performed by the operating system when applications make calls, so application program interface or system calls or application calls to the operating system. So in other words, when a application asks for some information or asks the operating system to do something, it typically happens at this session layer. Now, the important ones for us as networkers. Layer 4 is a transport layer. It's responsible for transporting the upper layers, so it says application layer payloads, but the upper layers, so layers 5, 6, and 7, this guy is responsible for the transportation of that upper level information from one host to another. And there are two main transport layer protocols which are typically around. So there's TCP, Transmission Control Protocol, and there's UDP, User Datagram Protocol. The point to get about these guys is that TCP is what is called a connection-oriented protocol. So in other words, it establishes and confirms that a connection has been made end-to-end before it transmits data. And if something goes wrong, it will retransmit. Okay, so it has ability to error detect and correct. UDP does not, so it's a connectionless protocol. So it basically sends information out. It's like almost like a bullhorn or a loud hailer system. It sends information out, doesn't know whether it gets received, doesn't care if it gets received, but it's a heck of a lot faster because it doesn't have that component of, are you there? Yes, I'm there. I've sent this packet. Did you get that packet? Yes, I got that packet. Can you send the next packet, please? It's just a broadcast. So it's a bit like a difference between a two-way conversation between two people and a single person like me talking to you guys without interaction, without any voice coming back. Protocols will add their own control information in an area at the beginning of the payload or beginning of the packet, the information that gets head out, and that's called a header. Okay, so each of those upper layer protocols, so application, presentation, and session layer, will add their own information relative or relevant to their own transmission, so what they're trying to achieve. And that's added on top of the transport layer stuff, and that's just simply called a transport header. Encapsulation is an interesting process, and that simply describes that process of adding that upper layer information to the underlying layer as it comes through. So that's taking the information from the top three layers and adding it at layer 4 and sending it out down to layer 3. Transport layer header addresses the receiving applicant by a number called a port number. So you will have heard people talk about port numbers, hopefully. If we think about port numbers related to networking, we can think of port 80 is web port, port 25 is SMTP, so that's mail protocol. 110 is POP, so that's mail client. Various other ports, and we'll have a look at, I think there's a slide and a couple of slides about those as well, which we'll talk a little bit more about more then. The other thing a transport layer does, if a message gets too big, it splits it up into smaller messages called segments and shoots them out one at a time, and then they reassemble it at the other end. So if, for example, and the reason that might be a problem is that if you're going across a WAN links generally have less ability to take large packets, and you've got to do some sort of cutting up of information as it goes across a WAN, whereas in a LAN environment, just a local area network, you're working at 100 meg or gigabit speeds or more. There's not that, and the size of the packets that it can take or the size of the messages it can take are much larger than in the wide area network world. So there's not that need to chop up the data stream. Network layer 3 is a network layer, and that's basically the one that's responsible in a nutshell for routing. That's it. So IP, so the IP part of TCP/IP lives here, and it owns it. It adds its own network layer, which always contains both the source and destination IP address. So the source address of the host that's transmitting, and the destination address of where that data is heading off to. IP relies on several routing protocols to find the best route for a packet in order to reach the destination. We'll talk about routing and routing protocols shortly. Basically, the idea is that they just build a roadmap of the network as it stands, and they work out, routing protocol will work out the best way for any particular packet to take across that network at any particular time. Data link layer, now we're starting to get into the hardware. So data link layer is really responsible for interfacing with the physical hardware or the NIC, the network interface card. The type of networking hardware or technology used will determine the data link layer protocol used. So example, are we using Ethernet or are we using Wi-Fi? Okay, two totally different data link layers, data link protocols, but still live at that layer 2. And link layer, we don't probably need to look at this just now, but the data link layer will encapsulate or wrap control information around the information that it's sending, just so we can keep track of what's going on. There's actually two layers to the data link layer, so it's split into a MAC, media address control layer, which is where the term MAC address comes from. So those little hardware physical addresses on your network interface cards, they live at the MAC address. There's also a logical link control layer, which we don't talk about in too much detail, and that's a little bit, that's more in control of the actual communication stream at this level rather than the addressing side of it. So we've got the addressing side of it, and then we've actually got the transmission side of it in those two particular layers, sub-layers. And then lastly, we have our physical layer. And this is basically the whole nuts and bolts of the physical layer is how do we get the information encoded so we can transmit it across the wire. So whether that's actually is a physical wire, it might be through the air if we're talking wireless, or it could be in a form of light across fiber optic cabling. So they're all the standards that do that ones and zeros electronic type level stuff. We have the concept of a protocol data unit, which is really just the technical name for a group of bits or group of information as it moves down the layers of the OSI model. So technicians loosely call this group of bits a message or a transmission, but the specific term for them is a protocol data unit. So we can see if we look at this nice little graphic here, we've got the OSI layer models split into 5 here. So we've got layers 7, 6, and 5 are often grouped together because they have very similar functions, as I said before. And that's just called payload and data at that level. And its extremely technical name is layer 7 PDU. The transport layer are either called segment if it's TCP or datagram if it's transmitted using UDP. Again, layer 4 PDU. Layer 3 network is called a packet. At layer 2 data link, it's called a frame, and at the physical layer, it's called a bit. So they're just different categories depending. So if you said to someone, I'm talking about a frame, they would know that you were talking about layer 2 information. If you said you were talking about packets, they'd be talking about layer 3, segments or datagrams at layer 4, and if you're just talking about payload or data, you'd be talking about everything, the whole lot. So it's just a little way, a bit of a sub-language within the language. So summary of how the layers work together, that's in graphical form. So the 2 points that I want you to get from this are, first of all, there's a concept called an interstack communication, and then there's a concept of intra-stack communication. So interstack communication, so between stacks, is really just the process of each of the 7 layers of the OSI model talking to their peer layer on the opposite end of the communication channel. Okay, so application will talk to application layer, presentation will talk to presentation layer, session to session, so on and so forth. Okay, that's inter-stack communication. Within a stack on a single device, so if we're talking about this browser here, intra-stack communication is a discussion between the different neighboring layers of the OSI model. So the physical layer can only ever talk to the data link layer intra-stack. Okay, so overall, let's classify it. So physical layer can only ever talk intra-stack to the data link layer or inter-stack to the physical layer on the next host. On the next host in the chain. So physical layer can either talk to data link on this host on the browser, or we can talk to the physical layer on the switch, and that's it. They're the only two layers he gets to talk to. The data link layer is a little bit more lucky, as are all the other subsequent layers. So all the layers above physical can talk to intra-stack, the layer directly above it or directly below it, and also interstack to the same layer, so in this case the data link layer, on any host or any device that the traffic passes through. So data link can talk to physical or network on this particular browser host, and it can talk to the data link layer on the switch, the router, and the web server. Okay, so and as we go up the stack, the same applies. So network can talk to data link and transport intrastack and any other network layer on any other devices it goes through. So depending on what sort of device it goes through, a particular layer may not have any need to communicate. Okay, so you can see here a switch, which is only a layer 2 device. There's no need for the network layer to have any conversation with any processors on the switch whatsoever. However, when it gets to the router, which is a layer 3 device, there needs to be some communication exchange. So complex, yes. Take some time to digest that diagram, and questions that you have about it, by all means, raise your hand or pop up on the forum. Okay, there is a good question I've just seen. So from Andronicus, what's the difference between data link and physical? Is a NIC physical and Ethernet data link? Yes, you are correct. So physical is all about ones and zeros and electrical or light or wireless signals. That's all it is. Simple encoding. The data link layer is, as I said, separated into those two layers. So logical link control, which talks to the physical layer. So that's a part of the data link layer that talks to the physical layer. And that manages that conversion of information from ones and zeros into actual electrical signals, for example, or light signals or wireless signals. The other part of the data link layer is that MAC address. So the address, the actual physical address that's on the NIC. So it's also an addressing component. So Ethernet as a whole is a data link standard. So it talks about addressing and it talks about logical links control. It encompasses both of those. Whereas physical is just about that ones and zeros, those electrical signals. So how the layers work together again, we can see this is simply just the previous slide in a Word format. So I'd urge you to look at these two, this slide and the previous one together, spend a bit of time digesting the information. If you've got some questions about it, pop them up on the forum. Because I kid you not, these two slides are basically a whole topic, or almost a whole topic in our networking subject. We really go into detail for it. That's one you've really got to join in on. Okay, so if we now look at some of the hardware that we're going to look at over the next few weeks. So switches, so these big guys here, we've got some. It's interesting, there's a range of switch sizes here. So we have some chassis-based switches, we have some fixed configuration switches. So fixed configuration switches basically have a set number of ports and that's it. Can't get any more ports, can't get any less ports on that particular switch. If you buy a 24-port switch, it will always be a 24-port switch. However, if you buy one of these big chassis-based switches, they have a number of blades in what are called blades. So they are literally shelves within the switch that can pull in and out. You can customize those to your heart's desire within the technical constraints of the chassis itself. So you can either fill them all full of ports, or you can have fiber, you can have copper, you can have wireless, you can have security modules, you can have all sorts of different combinations in there. So clearly they are for big enterprises, big deployments. Switches are basically connectivity devices that subdivide a network into things called segments, not to be confused with a TCP segment. Different segment, sorry for the confusion. It's not my fault, I didn't make the term up. Traditional switches will operate at the data link layer, so layer 2. Modern switches, however, can also operate at layer 3 and 4. So you often hear the term layer 3 switch. It's really just a router and a switch in the same box. That's all it is. Switches interpret that MAC address information, so the address that lives at layer 2. Okay, so the MAC address, 12-digit hexadecimal address that is burned into our network information cards. Common switch components that you'll see will be an internal processor, so basically a CPU, lots of memory, typically bucket loads of memory, particularly for the big chassis-based boys, lots of different ports, so fiber, copper, wireless, whatever, and an operating system, which is really what Cisco sell. Okay, so Cisco talk about selling switches and routers. No, they don't sell switches and routers. They sell an internetworking operating system. They sell iOS, that's what they sell. The hardware around that is just a means for them to sell that software. Okay, either one is useless without the other. But their core business really is the software. To install a switch, really, it's not too difficult, but you need to follow the manufacturer's guidelines. General steps, if we're talking about Cat5 or better UTP, so structured cabling systems, verify where you want to place the switch, turn it on, verify that it actually powers up and you can see something happening. Configure it if necessary. So if it's a Cisco switch, you'll definitely have to configure it. If it's just something that you bought at your local Home Depot or Officeworks, then you might not have to do anything. You just plug things into it and away it goes. Connect your devices or NIC to a switch port. Repeat for all the different devices you have. Turn all the nodes on. Bingo, away you go. Simple as that. Then we can connect to another switch to a larger network if you wanted to do that later on down the track. Simple as that. So a single switch installation, pretty straightforward in most cases. Switching methods, so the way in which switches pass traffic through them. Okay, this is important to have a basic understanding of. It is different, there is a different across switches depending on the vendor and how recent the switch has been made. There are 4 switching modes which exist, but we're only really going to talk about 2 of them because they're the 2 main ones that you're going to see. One is cut through mode and one is store and forward. So in cut through, the switch will read the frame's header. Now frame, remember, if we're talking about frame, we're talking about layer 2, aren't we? So the switch will read that frame. It will only wait for a little bit of the frame to come in before it decides where that information has to pass out. So you can see it very quickly, so you don't have to wait. In an Ethernet world, the packets or the data that you can send can have a maximum size of 1,514 bytes under normal circumstances. In a cut-through switch, it will only read the first 14. So it doesn't care about the other 1,500. All the valuable information from a layer 2 perspective is in the first 14 bytes. Once it has that information, it'll say, righto, I know where it's got to go, sends it on its way. So it doesn't worry about anything else that happens. The problem with that is that it doesn't get far enough into that information to verify that the data integrity of that packet is actually right. It doesn't get far enough. So it can't detect if packets have collided and been broken up and they're erroneous. So that's a disadvantage. So it's a lot faster because it doesn't look at everything, look at all the information, it just sends it out as soon as it knows where it's got to go to. So it can't detect corrupt packets. It's quick. Disadvantage is it will buffer data. So if the switch is flooded with traffic, not good. And it's best used in small work groups where you need lots of speed, or if you haven't got many devices. Okay, use cut-through switching, no worries. The other one is store and forward. And in this case, the switch will read everything into memory first. So it can check the whole packet as it comes in, decides whether it's okay, decides where it's fit to transmit on, and then it sends it out. Okay, so it's slower. It's a lot slower than cut-through mode. Now, when we talk about a lot slower, it's measured in milliseconds rather than seconds or minutes. So is it really going to be a huge notice to us? In most of our cases, no, not at all. But it can if you're a network engineer trying to engineer a specific solution in your network. So it's a lot slower, but it's a lot more accurate. It's a lot safer. Best used in larger LAN environments or a mixed environment. Okay, we've got lots of different technologies. The other advantage it's got is that it can transfer data between different types of different speeds of segments. So from 100 meg to 10 meg. Okay, cut through switches, not so much. VLANs and trunking. Okay, so VLANs are a construct which basically allow you to break down your network into smaller, more manageable parts. So a VLAN is a virtual local area network. So we talked before about local area networks, which are a physical network that's contained within a single site. We then have this virtual or logical construct of the VLAN. Okay, so they allow you to separate LANs into smaller logical components. They allow you most importantly to group ports on your switches into what are called broadcast domains. So a broadcast domain is an area of a network where broadcasts will propagate to. Okay, now if we don't have VLANs, if we just have a single flat network, a flat VLAN network, broadcast from a single machine will propagate to every other connected host, and everyone else has to stop and listen to that broadcast to determine whether it's for them, whether they need that information, and then continue on processing. So if you've got a large network with lots of broadcast traffic, that can really cause some performance issues. So broadcast domain is that construct. A collision domain is slightly different in that a collision domain is a length of a network cable or a small area in a network where hosts that communicate or transmit information at the same time can potentially have those transmissions clash together electrically and become damaged. And when that happens, that's called a collision. When those packets collide, they're called a collision. If that happens, then we end up with lots of packet retransmissions and we get slow performance because there's lots and lots and lots and lots of collisions and packets have to be retransmitted time and time again. Both of those combinations are really, really bad. So a switch is a great device in that it will provide a single collision domain for every port that it has. So if you have a 24 port switch, you have 24 collision domains, allowing you to limit the number of hosts you plug into that switch and have the likelihood for collisions to occur. Switches, however, don't care about broadcast domains. If they get a broadcast, they flood it out all ports and let everyone hear it. So they can be really, really noisy. VLANs come into that by existing on a switch, they're a layer 2 construct, exist on that switch, and they allow you to separate those different ports into different broadcast domains and thus lower the noise, if you like, of the traffic that's going around that network. We see an example here. We've got a couple of switches connected. We've got VLAN 1 to the left on the left-hand switch, VLAN 2 on the right-hand switch. Pretty simple setup, VLAN 1, VLAN 2. But you can have lots, you could potentially have 1,000 VLANs or more VLANs if you like, depending on your switch architecture and platform. Advantage of a VLANs is that they're flexible. So ports from multiple switches or segments, you can have ports from multiple switches or segments. The VLAN doesn't have to exist on one switch. It can exist on any number of switches in your network. You can transport it around any way you like. And you can use any node type. So you can have a wireless node, you can have a fiber node, you can have a copper node. Doesn't matter. Doesn't matter what the device is, you can share VLANs amongst any type of device. The reasons for using VLANs are manifest. They are separating user groups is one, to isolate specific connections for security reasons is another, to identify priority device groups to say, okay, well, VLAN 1 has priority over VLAN 2, for example, to group some other legacy protocol devices together. So we've got all these old machines over there. We don't want them talking to us, so they'll put them in their own VLAN. Or to separate your larger network into smaller, more manageable subnets. Switches by default will typically pre-configure with one default VLAN which cannot be deleted or renamed. It's also not very secure. So normally best practice would indicate we don't use VLAN 1 at all. We create other VLANs and use those. We can obviously create additional VLANs, indicate to which VLAN each port belongs, so we can assign our ports, our physical ports, to individual VLANs that we create. And then on top of that, there are a number of additional things that we can set up or configure or specify as well, including different security parameters, so who can talk, whether VLANs can talk to each other, through each other, filtering instructions, so what devices can go onto what VLANs, port performance requirements, so in terms of how quickly a port will begin to transmit traffic, but also at what speed that port will transmit traffic as well. And there's some network addressing and management options, which we'll look at more when we talk about routing. And typically, well, well, not always, but generally you would maintain the VLANs using the switching software, so the actual software on the switch itself. There are some solutions that are offered by different vendors that allow you to centralize that management through another service, so like that client server architecture we were talking about earlier, but most of us as network professionals would simply use the switch software to do so. Potential problem. If we're not careful with the way we put our VLANs together, we can cut off members of the group from the rest of the network. And the reason that is because once you start creating VLANs, you have to have some sort of layer 3 device. So whether that's a router or a layer 3 switch or a firewall or some other device that is capable of routing in order for those VLANs to talk between each other. If you don't do that, then you can create as many VLANs as you like. And technically and in theory, they cannot talk between each other. Now, I know some of you out there will say, but they can. I know ways it can be done. And yes, there are ways that can be done, not best practice, and generally they're because of security flaws. So generally you will need a router or some other layer 3 device to talk between VLANs. Now, trunking is merely and quite simply the ability to configure a link to carry multiple VLANs. So instead of just being a member port of a single VLAN, it has the ability to carry information about all VLANs that exist on that switch backwards and forwards across that link. And normally you would configure that ability on links between switches, which we'll have a look at in the next slide. Physically, a trunk is just a single connection between switches. And the thing to understand, the VLAN data separation comes from the fact that if you are a member of a VLAN, any information or any packets or frames that you send through a switch will be tagged with that particular VLAN number. So if you're a member of VLAN 2, all your traffic going through that switch will be tagged as VLAN 2, thus meaning that you cannot communicate with any other VLAN unless you go through a router or some other layer 3 device. So here's an example here where we've got a couple of switches with 1, 2, 3, 4 VLANs on it, and you can see here we've got multiple hosts in different VLANs, and some will talk to each other. We've got a trunk port here configured with VLAN 1, 2, 3, and 4 information. So that simply means that that trunk port will enable all VLANs to be transferred across that particular switch. If we didn't have that trunk port there, VLAN 1 and 2 would be isolated on this switch, on switch 1, and VLAN 3 and 4 would be isolated on switch 2. Now that we have that trunk port, we can share those VLAN mappings between those two switches. Now, of course, in theory, these devices still can't communicate directly to each other because we don't have a router. But again, we look at that more when we get to routing. So spanning tree protocol is the next thing, it's the next sort of cab off the rank. It's an IEEE standard, and basically, again, it operates at the data link layer, so same level as VLANs, and its whole purpose for existence is to prevent traffic loops. So in other words, you can have loops, physical loops within your network that you create with physical cabling. It's spanning tree protocol's job to stop those loops from being anything other than just used for redundancy. There are 3 steps to coming up with a spanning tree, and we might have a look at them in conjunction with this particular slide here. So we can see here we've got a number of switches. We've got a number of inter-switch links. You can see that there is clearly loops between these switches. So between C, B, and A, between A, B, E, and D, and between D, F, and E. Okay, there's loops everywhere. That's great for physical redundancy. So if we lose links, we can still keep communication up. But however, if we don't have spanning tree protocol managing our tree or our loop, our logical loops, we could potentially have a packet come out of this switch port, head down to here, back down to here, doesn't have the host that it's got to go to isn't on, so it doesn't know where to go, and it keeps looping around all over the place, basically forever. Okay, once that starts to happen, that creates something called a broadcast storm, which overwhelms switches very, very quickly, regardless of how much processing power and memory they've got. So spanning tree builds a loop-free topology. So in a nutshell, it basically says, all right, we've got loops here. This is the best or fastest link. I'm going to block those 2 paths. So the only way I can transmit down from F to D is to go via E, B, A, and D. Okay, so it looks like it's going to take longer, but the algorithm that spanning tree protocol uses to determine which paths are blocked and which paths are open is very complex and works out the most efficient loop-free path in the network. So you can see that in this particular case, the tree has decided it's going to block here, here, and here. We now have a totally loop-free path, but if we need it, we have 3 other links that can come up if we lose one of these other physical links here. So for example, if we lose the link between switch F and E, the link between F and D will be reinstated and come back up again. And then we have a loop-free path. So in a nutshell, that's what spanning tree basically does. It does that, it generates the tree, it blocks the paths based on a very complex algorithm, which is based on the actual, a thing called a bridge ID. So a bridge ID, or bridge, is just an interchangeable word with switch. Basically takes the MAC address of the switch and a priority value, which is set to 32768 by default, but can be manually changed. It basically takes those 2 components, puts them together, and whichever has the lowest value basically becomes the root, or the king, if you like, of the spanning tree. And then all the other switches, all the other links are blocked or left open based on the particular flow of information from that single switch. And we'll look at some examples. There's some examples in the resources that you take your time going through and have a look at some of those resources. There's also, I think, a lab in the first week to do with spanning tree as well, so it's worthwhile having a look at that. It's quite complex. The theory behind it is quite complex. So if you have questions, have a look at those resources. When you have questions, which undoubtedly you will, put them up on the forums and we'll generate some discussion about it. It's not really something you can, it's a whole subject on its own. I actually have a book here sitting on my shelf, which is 1,800 pages thick, just on spanning tree. So it's quite complex. The history of spanning tree, just briefly, introduced in the 80s. Originally it was too slow. The original version of STP was too slow, so they came up with this rapid spanning tree. So a newer version, 802.1 standard, it allows these links to transition, the elections to happen more quickly, and links to transition really, really quickly. So we still have that redundancy, but instead of taking a long time to recalculate when we lose a link or get a new link, it now does it almost instantaneously. 2 vendors, Cisco and Extreme Networks, have proprietary versions. That means it only works, with their own switches. It won't interact, it won't play nicely with others, which is typical. And basically, there's no enabling or configuration needed look, I'd nearly argue with that, but I'm going to go with it because it's on the slide. No enabling or configuration needed in typical situations because it's all built into the actual switch operating system itself. Now, if you're a real geeky sort of network engineer, you will want to make sure that you know what spanning tree is doing. So the least amount of thing that you will want to do is actually configure a specific switch to be the top dog. Okay, that's probably the most important thing you do. Outside of that, you're probably going to let spanning tree take its own course and work itself out. Otherwise, it becomes a bit dangerous. If you start changing timers and the way traffic's going to pass around, you can sometimes be a little bit too clever for yourself and get yourself into more trouble than what it's worth. So content and multi-layer switches alluded to before. So we can also have these things like normal switches will live at layer 2, but we can also have layer 3 and layer 4 switches or content switches. And basically all they do is they're really extra functionality that's bolted onto a simple old switch. So we take a router and a switch and we put them together and we get a layer 3 switch. We take, a layer 4 switch. So layer 4 switches look at TCP and UDP, and we bolt that little functionality on, and now it becomes a layer 4 switch. And then we have our application layer, application switches, which will look at everything in the communication stream in order to decide which way your transmission will filter. The advantages of these is that it's really advanced filtering. So you can look at every single part of your packet and make a decision on which way that packet's going to go based on that high level information rather than just on MAC address, which a layer 2 switch does. You can keep bucket loads of statistics for all the different layers. So that's kind of cool if you're a bit of a management nerd. And there's some security functions as well built around particularly the layer 7, so the content switches that allow you to secure things much more securely because you have visibility into a greater portion of the information flowing through your network. They distinguish between layer 3 and layer 4. A distinguishing feature between layer 3 and layer 4 switch is basically manufacturer dependent. So some people call them layer 4 switches, people still call them layer 3 switches. So layer 3 switch is technically really something it just routes as well, but because you've got that TCP UDP at layer 4, some people drag that in and they'll sort of call it, oh, let's call it a layer 4 switch because that'll allow us to do a bit more marketing and sell some more product. But technically it really does the same sort of thing, similar sort of thing. These higher layer switches, of course, as you would guess, will cost more than layer 2 switches, and typically they're mainly used inside a network backbone, so we don't take them outside of that simply for cost effectiveness, but also for speed as well, because the closer you get down to the end user, the faster you want to be. Okay, in terms of response time to their communication needs. Across the backbone, yeah, you've got lots of bandwidth, you've got lots of memory, you've got lots of processing power, lots of backplane, but at the same time, you've got all this complexity built in there, but you can afford to have it there because you've got that extra memory and processing power. As you get down the chain, it becomes more difficult to service, in most cases. So routers, if we go to the next layer, so next layer up, layer 3, routers are a multi-port device which simply distinguish between our network subnets. They join LANs and WANs together, so local area networks and wide area networks together, but they can also just join LANs together. And the good thing about them is they can handle different transmission speeds and protocols. So you can have on one side a 10 meg Ethernet interface and on the other have a 256K frame relay connection, or on one side you can have 100 meg Ethernet, on the other side you can have a ADSL2 link or an ATM link or a fiber link. Doesn't matter. Routers don't care. They're happy to work with anyone. Key thing, they operate at layer 3 of the OSI model. They direct data from one segment or network to another, so you need them to talk between subnets, you need them to talk between VLANs. We have logical addressing, so our IP addresses, whether they're IPv4 or IPv6, live at this level, and they're protocol dependent. So what that means is you have to have a specific protocol stack on them in order for it to work. So they're dependent on IP4 or IP6. So you can't run, they're not just generic, they won't just take everything at one time. You actually have to have that protocol stack enabled and configured. They're slower than switches and bridges because they've got to look deeper into the packet, deeper into the information. So they work at layer 3, so of course they're going to be slower than the switch, which only works at layer 2. It doesn't have as much information to read. Unless you're talking about content switches or layer 3, layer 4 switches, in which case the difference is moot. They traditional standalone LAN routers are being replaced by layer 3 routing switches, and that's simply because there's better performance out of a layer 3 switch in most cases now than what there is out of a single router. The new niche for them is in specialized applications, so linking large internet nodes together or completing digitized telephone calls, those sorts of applications. So characteristics and functions, they have intelligence, so they can track node location, so another end node, end station location. They can determine the shortest and fastest path between two nodes, and they do that via the exchange of routing information through routing protocols. And they connect dissimilar network types. So as I said before, LAN to WAN, Ethernet to frame relay, Ethernet to ATM, wireless to Ethernet to ATM, whatever the case is. In large LANs and WANs, routers are, well, they're not indispensable. They're just a must-have. You have to have them. Otherwise, the whole idea of that broadcast traffic just simply overwhelms the networks. Components include internal fast processors, internetworking operating system, lots of memory, input and output ports, and a management control interface, usually via CLI. Multi-protocol routers generally have multiple slots or multiple ports, and they'll accommodate a multitude of network interface types. Okay, they're the big boys, the ones that exist in enterprise and ISP, so service provider land. Inexpensive routers, home and small office use also exist. You'll see them dime a dozen. Get them at Officeworks, Home Depot, Walmart, wherever you want to go. Typically in the home and small office, as I said. So here's some big guys here. So on the left here, we have a Cisco chassis router, a Juniper, and a Huawei. So they're big, they're service provider or really big industrial strength type routers. Over here we have some smaller ones. So these are 2900, 3600s, 3800s probably. I'm not sure how old that diagram is, but they're not fixed configuration. You can see just these little silver slots on the front of this guy here, the top one. You can fill them with different interface type cards. But they're certainly less configurable, less expensive, less memory, less processing power than these guys down here, the chassis-based switches. So the difference between these guys down here on the right and these guys on the left is these are carrier grade. So think Telstra, Optus, AT&T, so on and so forth. These guys down here are enterprise level. So think National Australia Bank, Commonwealth Bank, internal Telstra networking, that sort of stuff. A lot of this Cisco, these are chassis-based switches that can have the big blades pulled in and out. These guys are module configuration, so they take little modules, but certainly not to the same degree as the chassis-based switches, chassis-based routers there. These guys here too, down on the right, some of those are also layer 3, layer 4 switches as well. So you'll see these multi-port blades here. Just point this out just because it's interesting. Well, it's interesting to me anyway. Multi-port blades here are the switch component, and then there's some processing power in these ports down in these blades down here, which is where the routing nuts and bolts and brains occurs. So kind of cool to look at. Big, bulky, noisy, use bucket loads of power, but a whole heap of fun to work on. Not that I'm biased, of course. So router capabilities, as we said before, they connect to similar networks, interpret layer 3 addressing, so that IP addressing, determine the best path, and they reroute traffic. Optional functions including, well, they're not optional really, they do filter broadcast transmissions. You can enable custom segregation and security, so you can determine who can flow through what and which way it can go. It'll support simultaneous connectivity, so lots of different things can happen at once. Fault tolerance is clearly there, particularly if you've got more than one chassis. They can monitor network traffic and diagnose problems and trigger alarms automatically based on configuration that you put onto them. So pretty good. Number of different classifications. So we've got an interior router, which is just a router that lives on between a couple of LANs. So small guy, doesn't do too much, has a bit of fun, connects a couple of LANs. An exterior router is a classification of a router that will sit between a LAN and an external network. Some external network doesn't have to be a WAN, doesn't have to be the internet, can be a partner, a business partner or an integrator. Border routers will connect LANs typically with WANs or the internet. And the concept of a routing table really is just that. It's basically the map of your network. So the map of all the different subnets and networks that you have within your network lives in that routing table, allows the router to determine which way to send packets when the time comes. Some static routing. So a static route is simply a route that is configured manually on a router by you as an administrator. So you tell the router how to get somewhere. Dynamic routing is where the routers speak through a routing protocol together and they bring up that whole concept of routing path, routing table. They build it themselves and they build the roadmap. The static routing is when you build a roadmap. In terms of installation, it's really simple for a small office or home office. Often for your internet connection, you'll get it sent to you pre-configured and you're good to go. When you're talking about a enterprise, it can be extremely challenging. Just an example of some routers there. So this guy here is an internal router. This guy here, or these two guys are internal routers, and this is your border router here, because we're going from the LAN here, collectively what's called the LAN, out to the internet. You could also argue that this one's an external router here as well, router B. So you've got a couple of LANs connected through a couple of routers and then out through the internet. So pretty basic configuration setup. Then if we talk leading on to that, we're just talking about routing protocols. So there's two types of protocols that we often talk about in routing that sometimes get confused. There's a routed protocol, which is something like IP or IV6, so it's the addressing component. Then there's a routing protocol. And a routing protocol is a protocol that helps to build that roadmap of our network. So they determine the best path. That is the most efficient route from one node or one network to another. How that path is built is determined by a lot of complexity And again, there's some resources available for you to look at, and we'll talk about it more as we go along. But it's basically dependent on how many hops there are between networks, the current level of network activity, so the utilization of that network, whether there are any unavailable links or links that are going up and down, so flapping, the network transmission speed, so how fast the links are between all these networks, because they're not always the same speed. There can be very different speeds. If you think about going from LAN to WAN to WAN back to LAN again, you've got fast, slow, slow, fast. Okay, so there's varying speeds across that network. They need to be able to depend on that as well. And lastly, the topology. So how is it connected? The best path is determined by the routing protocol. So the dynamic routing protocol that is being used. There are a number of metrics that routing protocols use. So a metric is basically just how are we going, what is the cost, or what is the factor that we're going to apply to a route to determine whether it's best or not, how good it is relative to any other route. So I can use a simple number of hops. So how many routers or how many different devices does it have to get through to get to the destination end? Number of hops. Throughput on the potential path. So in other words, how fast can we get through, or how much available speed there is. Delay on the potential path. So what is the likelihood that packet's going to get delayed for whatever reason it is? So it could be just latency. So as a cable gets longer and longer and longer, basic physics tells us that it takes longer for information to pass across that particular link. So that's a delay. So obviously over a WAN link with a very long length, you're going to take longer to get across that than you would over a short LAN link. Okay, so delay on potential path, that's also considered in terms of the routing metrics. The load, so the overall traffic that's on a particular interface or router at a time. Maximum transmission unit, so that's a contract where that is basically says how big a packet we can send over a particular path. So in Ethernet, as I said before, it's 1,514 bytes. That's the biggest packet you can send. But when we get to, say, ATM, a synchronous transfer mode, which is a WAN technology, we can only send a maximum of 53 bytes. So we've got to chop our 1,514 byte packet up into lots and lots of little packets to send it across our ATM link. Okay, so that's a consideration. Cost is a consideration. So cost is one that, say, a protocol like OSPF uses. And it's basically just comes down to the speed of the link. So is it a 10 meg link, a 100 meg link, a 50 meg link, whatever. And then lastly, the reliability of potential paths. So how often is it up? How often does it go down? Another important concept is router convergence time. So that is the time that it takes all the routers within a network to recognize and to get to build the same version of the roadmap, if you like, the routing table. Every time there's a change or a network outage, so a link goes up, a link goes down, new routers put in, the routers have to reconverge. So they have to get that consistent picture of the network topology back again, the network paths back again. The time it takes for that to occur can be slow with some protocols and really, really fast for other protocols. We'll have a look at that in just a second. In fact, we'll have a look at it now. So there's a couple of different types of routing protocols. There's a distance vector routing protocol, which is basically determines the best route based on just some really simple factor like a hop or a latency or other network traffic conditions. It's just a real simple distance to a destination. So some examples of that are RIP, Routing Information Protocol. The only thing it cares about is hops. So how many hops, how many devices do I have to get through to get to the end host? It limits that to 15. Any more than that and it says, you know what, taking too long, I'm going to drop the packet, died. So you can imagine RIP isn't great for really big networks. It's also a type of interior gateway protocol. So that literally means it's used really more on LANs than over WANs. Okay, you can only route within internal networks. Use it for internal networks. It's slower and less secure than some of the other routing protocols that we're going to have a look at. RIP version 2 is also distance vector, generates less broadcast traffic, a little bit more secure, still got the 15 hop limitation, not so commonly used. We then have BGP, which a lot of you will have heard of. It's the routing protocol of the internet. Communicates using its own specific messages. uses a bucket load of factors. You could do literally, I've got another big fat book sitting up on my shelf which talks about just BGP as well. Massive protocol, massively complex, lots of different ways to determine best path, not something that's within the scope of this MOOC, that's for sure. But you can, it's highly configurable, so you can configure it to follow any number of policies, enabling you to do really sophisticated traffic engineering, which is why we use it on the internet. We then, as compared to the distance vector, we then have the link state routing protocols. In this case, instead of just basing the network table or the routing table on simple hops, we share the state of all our links. So each router understandably knows whether all its links are up, and it shares that information with all its neighbors. And so all neighbors know how everyone else is going, how healthy, if you like, everyone else is. OSPF, Open Shortest Path First, is an example of a link state protocol. It doesn't have a hop limit. It uses cost as its metric. It's got a really complex algorithm for determining best paths, which so we don't need to go into that much detail. Suffice to know that it simply uses cost as its metric. And with OSPF, each of the routers will maintain a database which shows the status of all its neighbors' links, of all its friends' links. Okay, all the routers within that routing domain will know how each other is traveling. And lastly, not really going to talk about it too much. It's intermediate system. It's a bit of a older routing protocol. I wonder if anyone's actually seen it out there. Probably some of you have seen it, but certainly not very common. Supports only 2 layer 3 protocols, IP and an ISO specific protocol, less common. OSPF is probably the routing protocol of choice for interior routing protocols. BGP, obviously, the routing protocol of choice for exterior networks or those on the internet. Hybrid guys, good old Cisco, as usual, have to come up with their own thing. They came up with a thing called Enhanced Interior Gateway Protocol, which was a combination of link state and distant vector characteristics. Go figure. EIGRP is the most, they've also got one called IGRP, which is just EIGRP without the enhancements. EIGRP is the most popular, only works on Cisco routers, of course, it's proprietary. They allege that it's got faster convergence time, lower network overhead, easier to configure, and less CPU intensive than OSPF. Well, I beg to argue maybe the less CPU intensive, but easier to configure. That's a moot point. Supports, multiple protocols, so it'll do IP, it'll do IPX if you still want to use that, and it'll even do AppleTalk if you want to use that. And it does scale to very large networks. I'll give it that. That's for sure. It's still used a fair bit. OSPF probably more common though. That's just a little table which basically gives you some a brief rundown on the routing protocols we talked about, the type, and whether they're an interior or exterior. So that's really just for your reference as well. Gateway is another multifunction device. So a gateway is basically normally a gateway is considered a combination of network hardware and software, and all they really do is they connect different systems together. So systems that use different formatting, comms protocols or architecture, a gateway will allow them to connect to each other and talk. So as we were talking about before, a router is really a type of gateway, but there are other types of gateways as well. They can reside on servers, normal computers, connectivity devices, i.e. routers, or mainframes, other devices like that. So they're just ways of translating between one format and another. Popular gateways include those that service email, internet, LAN, so different LAN protocols, different LAN technologies. So say for Ethernet and token ring, token bus, if anyone uses that ever now, to translate between voice and data. And of course, a firewall is a typical security type implementation of a gateway. We then have our cloud computing that we briefly need to touch on. We know that the internet is frequently pictured as that light, fluffy cloud, but what the heck exists in that cloud, most of us never get to see or know about unless you work in an ISP. And then when you do, that really blows your mind what is in behind the scenes there, because it's very different to what most people think about. So cloud computing is basically the flexible provisioning of data storage applications and services that are then provided to multiple clients over a provider network. Okay, we'll see an example of it in the next slide. The distinguishing features of cloud computing is that it provides self-service and on-demand services. It's elastic in that cloud can expand to expand in and out, so it can come in and out as need be depending on the services, number of customers, what we're offering. Certainly it supports any number of platforms. It allows you to pool resources, okay? So pool your RAM, your storage space, your network resources, your bandwidth, your speed, all that sort of stuff allows you to consolidate it and share it from a provider network perspective, and provides metered service. Okay, so that is you pay for a service and you get a certain amount of traffic or speed or data based on how much you pay. So here's an example of a cloud computing service. We have the cloud here. Within that cloud, we have a virtual server which has all these different functions and features on it, which you can then access from any location that can plug into that cloud, whether that is via the internet or via a direct link or a WAN link or some other link. And of course, you can use any other type of device that you like. You can use a tablet, a laptop, a phone, or a traditional desktop. And you can get access to it anytime, day and night, without issue. Obviously, these are provided by service providers, and they put billions of dollars into providing a resilient, fast system. There's lots of arguments for and against cloud computing and providing resources this way, but certainly it's getting bigger. It's certainly not getting any smaller. We can provide, as some examples, we can provide virtual desktops, so operating environments that are hosted virtually through the cloud. We can connect to those through thin clients, if you like. And these are provided through different physical computers than the one that your actual user interacts with. So it's just you have a thin client, which is the one the user interacts with. It shoots off into the cloud, grabs its operating system or desktop from another computer in the cloud, and away it goes. And the user just thinks they're sitting there nicely working away. There's lots of AAS, so as a service offerings. So there's network as a service, infrastructure as a service, software as a service, so on and so forth. Lots of cloud offerings, which we're not going to go into any huge detail with tonight, or probably at any stage during this particular 4-week course. Again, it's a whole topic, a whole subject on its own. Basically, the idea is that the service provider will offer customers a complete set of networking services. As an example, network as a service. And 2 types of delivery: through a public cloud, so accessible via the internet, or a private cloud, generally accessible through some sort of VPN or WAN link provisioning, based on how much you want to pay. And that, after a very long time, I do apologise. I told you I'd go over. I apologise in advance. I'm sorry. Leaves us with any questions that we want to answer. So, Guy, what have we got that we can answer, do you think?
Well, we've got about 24 questions.
Okay.
Okay,
there's a few of them I can answer pretty quickly.
Yeah, so I reckon they're all fairly simple. So I'll start with saying thank you very much for everyone for sticking around. The difficulty of condensing a 12-week subject into something that is coherent for a 4-week short course is a difficult task. And the introduction to all of the principles that we'll be talking about and concepts and hardware that we will be talking about over the next few weeks did require a bit of extra effort. I would expect that you should budget 90 minutes for each of the subsequent lectures.
Yeah, I would agree. We're a bit longer tonight because of the intro, so yeah, 90 minutes would be good.
Yep, and apologies for not considering that before knowing that it was a Mat C and a networking short course. We should have advertised 90 minutes, and I'm sorry for that. But that said, as the chat will attest, there's a lot of people that are getting a lot out of it. I'm very sorry for those that have had to go away, or it's too late, or it hasn't fit into their schedules. And I do apologise for that, but there will be a webinar recording coming up. And with that in mind, if you would like to stick around for the Q&A, we'll rush through them now and probably be done in about 5-10 minutes.
Okay.
For those of you that do need to go, that's okay too.
All right, so I will start right at the top. So will there be content on troubleshooting network issues? A little bit, but more of that will be more provided through the resources on the site rather than the tutorials. Is bandwidth and internet speed interchangeable? For the purpose of this course, yes. So there are some slight technical differences, but the terms will be used interchangeably in this course, yes. If I use home network in Windows, is that still point-to-point? Possibly. It's more about how you share your resources. So point-to-point is sharing resources between every endpoint within the network, whereas client server is about everything being shared from a centralized location. So you can use home network. Oh, sorry, I'm thinking version, not, whoop, I misunderstood your question. Home network, yes, that's P2P. So I could answer that so much quicker. We'll be covering Google's Quick Protocol modeled on UDP. No. Same layer interactions, adjacent layer interaction. Yes, you could think of intrastack and interstack as those. Yes, Shane, that's a good point. Yep, so same layer interactions, adjacent layer interactions, correct. Can I ping to a MAC address? There are ways that you can ping in quotation marks, MAC address, but technically, specifically, the term really relates to ICMP, which is a higher layer protocol. So you really ping to an IP address rather than a MAC address. So switches are called, switches are called layer 2 devices and routers layer 3. That's because switches work at the MAC address layer, so they work at the hardware layer, whereas routers work at that IP layer. So they route using IP addresses, and all that operation occurs at layer 3 of the OSI model. So that's a distinguishing part between the two. VLANs fit into the OSI topology? Oh, that's an excellent question, Carl, and one that we could probably debate for a little while. They are, oh, wow. Look, my personal opinion, they're probably considered more of a layer 2 construct, but they definitely leak into layer 3 because they're also often spoken about in the same tone as IP subnets. Maybe not layer 4, maybe not that high. You could possibly argue for that, but I'd probably debate that one, but definitely layer 2, layer 3. Is a node simply a device? Yes, it is. Just a PC, printer, server, whatever. A node is just a generic term for any device that's connected to the network. Is store and forward similar to FEC? No. So if you're talking FEC, if you're talking fast ether channel, which I think that's what you're talking about there, no, that's store and forward is a way in which is methodology by which the switch will read in the information, determine which way it's got to go, and then send it out. So it stores all the information, reads it all, and then forwards the packet as a whole. Fast ether channel is about bundling ports together to create a faster bandwidth link. So you take 4 physical links, put them all together into a logical link, and it becomes 4 times faster. Okay, so combines the bandwidth of the 4 physical links together. As an example, it can be more, can be less links. Does a typical managed switch allow for a choice of switching modes? No. No, it doesn't. So you can't switch between switching modes. A switch will be manufactured with a particular mode, whether it's cut through or store forward or fragment free, and you can't change between them. And which one's more common will be depending on really on how old your switch is. So a little while ago, fragment free and cut through were all the rage, and now it tends to be more store and forward because hardware has got a lot faster, and they like the everyone likes the resiliency that the store and forward gives you, even though it is a little bit slower. So VLAN and VIP. VIP, I'm assuming you're talking about a virtual IP there. So a VLAN is a layer 2 construct, which allows you to segment groups of hosts into a separate area, if you like, layer 2 area. A virtual IP is an IP that is assigned to a virtual or a VLAN interface that is then used to route between VLANs. So it's a related but separate construct. So VLAN is layer 2, a VIP, a virtual IP address lives at layer 3. Is there any boundary or limit range for using port numbers in VLAN? Yes, there is. And again, that will be dependent on your switch vendor and the operating system that it runs. But for example, Cisco will allow you to use up to around about 4,000 VLANs on most of their products. There are some VLAN numbers within that 4,000 range that aren't usable because they're either legacy features or historical things that are hard programmed. But in around about the 4,000 mark. If you're in a network that's using more than that, you're in a pretty big network. Do trunk ports have to be configured on each switch individually? Not necessarily. There's a protocol in Cisco world called DTP, Dynamic Trunking Protocol, which will do that for you. But there are a number of different things that have to be in place in order for that to work correctly. So generally best practice would be to do it manually. And if that's the case, then it has to be configured on each switch individually, yes. Can you tell us about MLT's multi-link trunking? Probably save that for another time. That's a big discussion. So now's probably not the right time. Might be worthwhile if you want to talk about that, post on the forum and we'll address it there. I think that's probably a better place for it. That's a bit of a discussion there. Who decides the best path and decides the algorithms? The people who write the protocols, basically. So there's a number of different protocols, which a number of different underlying algorithms that go into routing protocols. So for instance, OSPF uses what's called the Dijkstra algorithm, which was created by Dr. Dijkstra. And that's yeah, how they do that. Wow, you know, I mean, that's a discussion that's way out of my area of knowledge. But the underlying algorithm that the protocol uses is what determines that actual best path. And there's a whole heap of different things that we talked about. So the metrics, the speed, the delay, the latency, the cost, reliability, all the bandwidth, all those sorts of things that are fed into that algorithm to then determine the best path. Content, yep, F5 is definitely a content switch, or they make content switches. Not all their devices are, but they do make them. Are route tables dynamic or configurable? They are both. So if we use dynamic routing protocols like RIP or OSPF, something in that sort of realm, then they are dynamic. Or if you use static routing where you as an administrator type the details in for each route, then that becomes configurable. And even you could argue that even dynamic routing protocols are configurable from your point of view as well, because you can massage that routing protocol to behave in certain ways yourself. Most efficient route, if there are multiple routes for traffic travel, is if there is STP. Okay, so routing and STP are very, very different. So STP is layer 2, creates loop-free topology. Routes, multiple routes. If you've got multiple routes to the one location, there is different ways in which that can be handled. So you may, there might be multiple routes, but there is generally a best route. Okay, so you might have 5, it's like you think of it as a roadmap. There might be 5 different roads to get to a certain city, but there's usually a fastest road. And that could depend on time of day, depending on how much traffic. It might be physical length of the road. It might be weather conditions. It might be speed limit on that road, whatever the case may be. If you have a situation where you've got 2 routes with the absolutely identical cost, then some protocols will actually load balance. So I'll send packet per packet per packet over those particular links. Or is STP, yes, sorry, there you go, I should look at that one. STP is only within the LAN, correct. Can layer 3 switches fill the role of internal routers? Yes, they can. What is the need for an autonomous system number when choosing BGP? Okay, the autonomous system number is basically the identifier for your individual routing domain. So you as an organization, for example. So if you don't have those autonomous system numbers, and look, in fairness, organizations can have multiple autonomous system numbers, but they basically indicate a particular network or particular routing domain. So without those, everything will just be a hodgepodge. Is link state protocol vendor specific? No, link state, the concept of link state is not not vendor specific at all, no.
Sorry, Matt, just before you go on, I'm going to cut the questions off now. Any further questions, I will just delete.
Okay, fine, no worries at all. Thanks everyone. I really do appreciate your time. I know it's been a couple of hours, and that's a long time to sit and listen to me at the best of times. So thank you for your attendance, and I promise
Sorry,
next
Matt.
week will be a
Sorry, Matt.
little shorter.
Yeah, sorry, Matt. I was actually saying no further questions. Chuck your last questions in. We'll whip through these last ones. We've already gone.
Oh, okay, righto. Sorry. Sorry, no further questions. Okay.
No further questions. I'll cut them off now.
Okay, all right. So you have to listen to me for a bit longer.
Yeah.
Okay, so CLI is, sorry, I should have explained that. That's command line interface. So that just means basically a interface, a text-based interface that allows you to interact with the router. Difference between a data gateway and an internet gateway. If we think about a gateway as just a device that translates between two different systems or two different protocols, there's no real difference between a data gateway and internet gateway. A data gateway is, I'm not sure of your context, but a data gateway could be defined as just a gateway that translates between two LANs, two networks, whereas an internet gateway will go from a network or a LAN out to the internet. So it's specifically for that use. Puzzling over slide 36. Okay, what is the distinction between applications and application layer? Okay, application is something like an internet browser or Microsoft Word or your email client, whereas application layer is the top layer of the OSI model. So it's layer 7 of the OSI model, and it has specific functions that allow those applications to interact with it. So that's the difference. The applications are the actual software that the user uses. The application layer is a set of constructs, a set of processes that allows those applications to communicate to a network. Is there any port number range to use in VLAN? I'm not sure what that's asking. That might be similar to the question earlier about the number of VLANs. So the typical port range for VLANs is on most routers, most vendors, is 1 to 4096, but there are some exceptions to that. So don't take that, take that with a little grain of salt. Content switch, yes, is an F5 is a content switch here. We answered that before. What is a bridge? So a bridge and switch are interchangeable terms, so they're exactly the same thing. So when people say bridge, switch, same thing. How can we troubleshoot UDP connectivity? Is there a similar test tool as ping? There's bucket loads of, if you do UDP connectivity, a search on Google, you will find bucket loads of tools that allow you to test UDP connectivity. Basically, they're just applications that you can configure to use UDP at a specific port number, send it off to an IP address, and it'll come back and tell you whether that port is up or not, is active. So yes, in answer, there is plenty of tools that do that. Why can't we bring the printer name on the Windows print server? That's a question I don't know. I'm sorry, I can't help you with that one. Something's obviously broken. Do all switches use PoE? No. Not all switches use PoE. They are more expensive. So PoE, for those that don't know, is power over Ethernet. So it provides provisioning of power to things like IP phones. No, not all switches use it. That's based on feature set and price point. Difference between a layer 3 switch and a router is simply that a layer 3 switch will do it's basically a switch with routing capabilities, whereas a router just has routing capabilities, so it doesn't have that switching component to it. So it's a layer 3 switch is a switch and a router built in together. A router is just a router on its own. We dealt with QoS briefly. Can we explain how this is different to QoS? Are they different? Well, that is a pretty large question. The best I can do to say is that they are different, but they're related. So class of service is a subset of quality of service, if you like. So quality of service as a concept, there's a number of different ways you can classify traffic and handle traffic and manage traffic and prioritize traffic. Class of service is a subset of that, in that it is one of those ways in which you can classify or prioritize traffic. So they are different, but related. So QoS, subset of QoS. What is MPLS? Well, it's multi-protocol labeling system or service. That's probably as far as I want to go about it. If you think of it as being similar to it's like VLANs for WAN. Okay, so a multi-protocol just means it can use any number of protocols. Label just means it pops a label onto a packet, which is similar to what they do in VLANing. So that's MPLS is a massive topic, a huge topic on its own. So I probably won't go into more detail than that. But it's if you think of it as being VLANs for WANs or VLANs on steroids. General home routers use which routing protocol? Often they don't use one at all. But if the ones that do will generally use something really simple like RIP. Very rarely will you see OSPF or anything like that. From a cyber security perspective, are some OSI levels more difficult to secure than others? Yes, they are. So layer 2 is probably, layer 1, 2, and 3 are probably okay. Layer 4 is okay. Layer 5 starts to get more difficult. Layer 6 is really difficult. And layer 7 is more difficult again. So as they go up the layers of the OSI model, they become more complex. The layers become more complex and they get closer to the end user, which in itself is more complex. So as we go up the layers, it does become more complex to secure them. And that's not necessarily a continuum. There are some exceptions in that, but generally as you go higher up the OSI model, it becomes more difficult to secure layers. What causes the failure of packets sent from source to destination? Lots of different things. So it could be faulty transmission lines, it could be faulty transmitting devices, it could be collisions, it could be electromagnetic interference, it could be lack of power, it could be storms, it could be water inside pits that create noise. Literally, it's unlimited what the issues could be. So the actual issue that causes the transmission problem could be anything, but the basic idea is that some part of the packet is lost or destroyed. So that part of it's really simple. What the end result is simple. How we get there can be anything. What is best definition of 802.1b, etc.? 802.1b is not actually something that I'm familiar with, so I'm not sure I'll have to get back to you that. Maybe 802.1b, or I'm wondering if you're talking about 802.1d, which is spanning tree. But 802.1b, I'm not actually familiar with that as being a well-utilized network protocol. That's not to say it isn't. So let me chase it up for you. And if I find any information on it that's relevant, I'll pop it up on the forums. All right, that's it. Thank you. So again, I'll have to, before I know Guy will want to finish off, but I just want to say thank you again for taking the time to sit and listen, and I hope that all of you got something out of it in the least.
Thank you very much. And because I'm a soft touch, Hilo was asked several times, in a nutshell, the difference between a router and a VLAN. No more questions, by the way.
Oh, so we got one more. Difference between a router and a VLAN. VLAN is a layer 2 logical construct. A router is a physical device that basically acts as a roadmap for your network. So they are related in that routers use VLANs, but they are very different constructs. So one's layer 2, one's layer 3.
Beauty. Thank you very much. Thanks all of you for all of those questions. We got over 50 at the end. So
yeah, it was good.
Well done. What's on next week, Matt?
Next week, that is a really good question. I can't for the life of me remember. It's been that long since I've stopped talking that I can't think of what it is. I think next week we are, it's a bit embarrassing, I can't remember off the top of my head what it is.
No, that's all right. Next week we are basically talking about, I've got it up here.
Good, I'm glad someone's got it.
Essentially, we'll be talking about infrastructure.
Ah, yes, indeed. Okay. All right, so that's a pretty long one too, but I'll promise I'll make sure I get through that in 90 minutes at maximum next week. So just strap in and hold on, guys. It might be a quick ride.
Wonderful. Thanks so much, Matt. Thanks for your time. Apologies again to those that have had to duck out early.
Thank you, Guy, and Chantel as well.